Okay, so today we will start a new topic, which is radiative transfer in stellar interiors. Okay, now you see we have already discussed about the three stellar structure equations. Now what we need to do after that is to obtain an expression for the transport of radiant energy through the layers of the star, and that too in terms of density, temperature and your composition, right? So for that we will spend some time on the envelopes of stars, right? Okay, now you see, you remember the energy equation, right? Here, so this was the energy equation which we derived in our earlier lectures, right? Now here in this equation you see this quantity F is basically the heat flux through a surface. So heat flux through a surface of constant mass in the star. Now you see this heat flux can come from conduction, convection and also radiation. Today we will talk about the heat flow through radiation. Now you see, in order to talk about the transport of energy through radiation, we need to first define certain quantities. The first quantity that we need to define is one that describes the radiation field and the flow of energy through that field. Okay, so you see, so what is the heat flux? Basically, the heat flux is the total flow of heat energy through a surface integrated over all directions and wavelengths. Now to obtain this value, we need to look at the energy carried in a specific direction at a specific wavelength. Okay, now let us define, say, I lambda to be the specific intensity, right? And it is the power, basically power per area emitted from a surface area element, right? And that is dA into a solid angle d omega at an angle theta from the normal to dA within wavelength range lambda to lambda plus d lambda. Now you see, although this I lambda is not a vector, it is possible to draw it with an arrow to indicate the implied direction of the energy flow. So let me show you the plot. Okay, so here is the plot that I was talking about. So specific intensity, right? So what this figure basically shows you is the specific intensity I lambda and its orientation relative to the solid angle d omega here and the emitting area dA. You see, this is dA, emitting area, and this is the specific intensity. Understand? Now you see the specific intensity may vary with direction, and so in order to define a single quantity at a point in the interior of a star, what we will compute is mean intensity, which is more meaningful, and basically it will be defined as the average of this I lambda over all directions. So let me define it in a way here. So we define the mean intensity as here. So this is how we define the mean intensity. This is equation 1. Now you see, if the radiation field is entirely described by blackbody spectrum, so if your radiation field is described by blackbody spectrum, then what will happen? You see, what about the specific intensity? Of course, this specific intensity is isotropic. We know this from blackbody, and as a result, what we will have is this relationship: average is equal to just I lambda, and this is equal to your B lambda. And what is this? This is basically the specific intensity for blackbody radiation here. So this one is specific intensity for blackbody radiation, right? Fine. So till now we have described two quantities. One is specific intensity, and now we describe the mean intensity. Good. Okay. Now you see, what about the energy? Now the energy carried by radiation in the so there was a problem. Anyway, so now, yes, I was talking about the energy, right? So basically what we are going to do now is we are going to again visit our energy density and pressure due to radiation, and afterwards we will discuss the consequences of the local thermodynamic equilibrium. Right? Okay. So as I was saying, what about the energy? So you see, the energy carried by radiation in the wavelength range being lambda to lambda plus d lambda through dA in time interval dt in direction of d omega is then how much? Well, it is basically, it will depend on I lambda as well, right? You see, so this is the energy carried by the radiation. So this is our equation 3. Now what we can do is we can use this expression to obtain the energy density of radiation for a radiation field given by the arbitrary I lambda. So right, now for that let us consider a volume element that is projected. Let me show you. So yes, this is what I am talking about. So we will consider a volume element here. You see, dV. So volume element dV is equal to dA dH, and here you can see the path of the original radiation plus the radiation entering from an adjacent volume element. Here both things you can see. So we will consider a volume element that is projected normal to the emitting surface element dA, this one, so that dV is equal to dA dH. Now energy is emitted in a given direction theta, you see this direction, from the surface and will travel through this volume until it passes through the side. Over here it is passing. However, radiation from the, so here we have this part, right, but also another, you see another part is also coming from the side over here. So radiation from the adjacent volume will enter from the opposite side, and this will be replaced by this one. Consequently, we can set the time interval that this radiation spends inside the volume to be how much? Time interval dt is equal to dl by c, or basically dh. So this is basically dh by c into cos theta. Okay. So as a result, you see the energy within the volume due to radiation emitted at angle theta is, let me write it down. So energy within volume due to radiation emitted at angle theta is basically given by this quantity here. You see, just multiplied by this. So this is equation 4. Fine. Now what we are going to do is to find the total energy over all directions. So total energy over all directions, and this means including the radiation coming from the top of the volume as well. So here also coming from the top, and this is found by integrating over d omega, right? So let us do this, and then we will have this result here, and this is your equation 5. So basically we can recover the Blackbody energy density if we replace this I omega with b lambda, I lambda by b lambda. Then we will get your Blackbody, in case then we will have Blackbody energy density. Fine. Now what next? Well, you see, we already know that the pressure on a mathematical surface is related to the flow of momentum through that surface. Well, we can understand this by imagining that the mathematical surface is basically replaced by a real solid surface, and the momentum that would normally flow through the surface must now bounce off of it, reversing direction in the component normal to the surface. And this change in momentum amounts to a force on the surface. Thus, we can calculate the radiation pressure due to radiation field given by this I lambda by considering the flux of the component of momentum normal to the surface. So, if we take the surface element dA to lie in the xy plane, then the pressure is, you see, this quantity, equation 6. But we know that P is equal to E by C for photons, right? And so for each wavelength interval we will have these two relations, you see here. So we will have this as well as this relation. So let us give numbers to them, equation 7 and equation 8, right? Therefore you see the radiation pressure can be obtained from the radiation field using this relationship. We do the integrations. Let us do the integrations over all angles, and thus we will have our radiation pressure. Now you see the energy flux. This is basically our energy flux. Now this energy flux passing through a surface element dA is the net energy flow in the direction normal to the surface. Thus we can write like this. So this energy flux passing through surface element dA is the net energy flow normal to the surface, and as a result we can write this relationship. Now if radiation field is, again I am saying, is isotropic, then what? Then you see this phi lambda, this one, equal to 0. Therefore, if we want a non-zero flux of energy through the surface, I lambda must be a function of theta. So, if we want a non-zero flux of energy through a surface, then I lambda must be a function of theta. And why are we talking about this? You must be wondering. Well, the reason is simple. You see, in the sun, we know that the internal temperature is very high, of the order of 10 to the power 7 Kelvin. Outside, it is just 6000 Kelvin, right? And there is a net flux of energy. So basically there is a non-zero flux, of energy in sun, right? So we know that, and so using this basic formalism, what we have arrived at the conclusion is that indeed we have a non-zero flux of energy, and as a result this must be the case. So we have come to this conclusion. Fine. Now the next topic that we are going to talk about, so we have started discussing about the specific intensity, mean intensity, then energy carried by the radiation, and then we discussed about non-zero flux of energy, right, from a surface, through a surface. Then we must have this specific intensity should be a function of angle theta, right? Okay. So now let me talk about radiative transfer. Transfer equation. This is again a very important topic. Now you see, as radiation passes through material in a star, energy can be added and removed from the beam due to interactions with matter. Now energy is removed from the beam as photons are scattered into different directions and wavelengths or absorbed by atoms. Well, energy is added to the beam as photons are scattered into the direction of the beam or are emitted by atoms, right? So you see here I have just shown you the processes that add and remove energy from the beam as it passes through a gas. The scattering processes can both remove and add energy to the beam. Similarly, absorption removes energy and emission. So, absorption removes energy and emission adds energy. Right. Okay. Now, the equation giving the change in specific intensity as a function of distance traveled through the medium is known as radiative transfer energy. So, basically, it is an equation giving change in specific intensity I lambda as function of distance traveled through a medium. Okay. Now, in steady state, the change in I lambda in steady state the change in I lambda along a path ds through a gas of density rho is given by, you must concentrate now on what I am going to write. You see this relation, equation 11. Now here you see this kappa lambda, this is known as opacity of gas at wavelength lambda, and this J emission, there is a subtraction term and there is a, so there is a subtraction term and there is a addition term. This is the subtraction term, this is the addition term. And here what is this J lambda? J lambda is the emission coefficient of gas, again at wavelength lambda. Now if you divide by minus k lambda, then so dividing by minus k lambda into rho, then we will obtain the transfer equation or radiative transfer equation. This is equation 12. This is quite important. So this is the transfer equation. Okay, where you see, okay, so yes, where this S lambda is basically known as source function, and this is given as J lambda divided by kappa lambda. So it is basically the ratio of emission to absorption coefficients and is a measure of how rapidly the photons in the beam are removed and replaced by photons in the local vicinity. Now you see this opacity. Let me spend some time over it. So you see this opacity of the gas, it has dimensions of area per unit mass, and it arises from several different mechanisms. It is often strongly dependent on the wavelength of the photon and temperature of the gas. Well, the main processes that contribute to the opacity involve different interactions between photons and electrons, and they are described by the initial and final states. Now, I am not going into the details, but I am just specifically mentioning them. So the various sources of opacity are bound absorption, bound free absorption and free absorption. Now, what about bound absorption? You see, in this bound absorption here, this one, this process basically involves the absorption of a photon, causing the transition of a bound electron to a higher bound energy level in an atom. Clearly, you see, the strength of this absorption is highly wavelength dependent, but it also depends on the ionization and excitation states of atoms in the gas. Now we do know that the ionization and excitation levels are temperature dependent. So now, deep in the interiors of the star, the gas is completely ionized, and as a result, the bound scattering is only important in atmospheres. So this one is important in atmospheres. Now what about bound free? Well, this process occurs if a photon has sufficient energy to completely strip off an electron from an atom and ionize it. Now in this case, the absorption will have an upper bound on the wavelength based on the minimum energy needed to ionize the atom. But remember that all shorter wavelengths are allowed, as the extra energy can be distributed as kinetic energy of the newly freed electron. Now, so similar to the case of the bound absorption, the strength and the wavelength dependence of this absorption vary according to the ionization and excitation levels of the atom in the gas. And so, the opacity due to this bound free process is temperature dependent, and again this is also important in atmospheres. Now, next comes the free. Well, you know that a free electron cannot absorb a photon and simultaneously conserve energy and momentum. But remember, it is possible for a free electron to absorb a photon if it is in an unbound interaction with a nearby atom that can accept the excess energy and momentum. Now what will happen is that in this case the electron is free both before and after the absorption, and so the opacity is non-zero across all wavelengths. Of course, the opposite of this process is what? Bremsstrahlung, and this happens when a decelerating electron emits a photon. Now there is also another important source, which is electron scattering. Okay, now in the case of Thomson or Rayleigh scattering, a photon imparts some energy and momentum to an electron or atom and is deflected out of the beam, and may also have its wavelength change. Just like your free absorption, this process is also applicable across a continuum of wavelengths. Fine. Okay, now let me come back to our discussion. So you see, this quantity, this kappa lambda into rho, this has a dimension of length inverse, and this can be thought of as the inverse of the mean free path of a photon of wavelength lambda in a gas of density rho. Now, a dimensionless quantity called optical depth, this we will define, and this will be defined as, you see, d tau lambda is equal to minus kappa lambda rho into ds, equation 13. Now this optical depth is basically a measure of the transparency of the gas. So this is a measure of transparency of gas. Now usually the optical depth is measured backwards along the direction that the energy is being transported, and that's the reason of the negative minus sign. Now it can also be thought of as giving the number of scattering or absorption events that a photon will have experienced during its passage along the integrated path. Now we can then write the transfer equation in terms of the optical depth to obtain this relation. You see? So, transfer equation in terms of optical depth here. So this is the new relationship, equation 14. Now you see, we are interested in finding the radiative energy flux through surfaces of constant radius or mass. Therefore, we want to solve the transfer equation for a specific intensity. So we want to solve this for I tau r theta. And what is this tau r? Tau r is basically tau cos theta. Let me show you here. So this is what I am talking about. Here you can see that the radial optical depth line element, you can see, and also this is the radial optical line element, and also its relationship to the true optical depth and the direction of the specific intensity beam for a small surface element inside the star. Okay, so now you see, we want to solve the transfer equation for the specific intensity, this one. Now we can do this through the use of an integrating factor applied to the differential equation. Let me show you. Here, this is equation 15, where now let us use e to the power minus tau r by cos theta as integrating factor, and then after performing some in algebra, you will find that we will get this relationship here. This is 16 and this one is 17. Now this equation here, it can be integrated to obtain the desired expression. The limits of the integration, what will it be? It will be from the surface of interest down to the center of the star. Now technically we need to know the optical depth at the center of the star, but we can take it to be infinity for all reasonable stellar models. So the solution it gives us, let me write it down in a separate page. So the solution is basically this relation here. This is equation 18. Okay, so let us now focus to find a sensible value to S lambda. Now, what is the interpretation of this equation 18? Well, you see, the interpretation of this equation is that the specific intensity at any given optical depth. So, specific intensity at any given optical depth is a, this is important, weighted sum of the source functions. You see, source functions from all lower depths, and the replacement of this intensity with the local intensities at each intervening layer. Just a second. Okay, there is a correction. So basically interpretation. So interpretation is that the specific intensity at any given optical depth is a weighted sum of the source function from all the lower depth in star. Right. So this is what I wanted to say. Now, what about the weighing effects? This weighing. Basically, the weighing, so this is weighing effects. So this basically, it has two effects. One is this one, the replacement, right? One is the replacement of the intensity with the local intensities at each intervening layer, and another effect is the gradual extinction of intensity from greater depths. Okay. Now at large optical depths, the weighing strongly favors nearby layers, and the mean free path of the photon is short enough that the source function can be approximated by a Taylor expansion. So at large optical depths, let us do a Taylor expansion of the specific intensity for the blackbody radiation. So what I am saying is that at this large optical depth, this weighing, basically this one, this term e to the power tau r minus t by cos theta, these ones, they strongly favor nearby layers, and the mean free path of photons is short enough that the source function can be approximated by a Taylor series expansion. So source function approximated by Taylor series expansion of specific intensity for blackbody radiation. So let us do this. Okay, so we have done the Taylor series expansion, and this is what we get. This is equation 19. Now this term is very important. So if we use this source function, then what about the specific intensity? So if we use this, then the specific intensity, it becomes basically this term. So source function, and if we use this, then specific intensity, it becomes this function. Now we can perform the integral by making a change of variables. So let us do a change of variables to u is equal to t minus tau by cos theta. And also note that gamma of n plus 1 is equal to 0 to infinity u to the power n power minus u du. Right. So if we note this after this change, then what we will obtain finally is this relation. Here, this is what we obtain. Equation 22, specific intensity, expansion, Taylor series. So, specific intensity expansion following Taylor series. Now, we want to obtain an expression for the radiative heat flux using this relation. So, we want to obtain an expression for radiative heat flux. Now you see, at large optical depths, we need to consider the leading non-zero term of the expansion. So, at large optical depth, we consider leading non-zero term of above expansion. Right. And so, you see, so if you use equation 10, well, what was equation 10? Let me again write this down. So this was the equation 10 that we previously wrote down. Then what we can do is we can do this expansion. So we will use this and putting it over here. So using equation 22 and 10, and then equation 22, what we will have is this relationship here. This relationship, you see, I am putting this here, and this is equation 23. Now, note that only odd values of n survive, and so the leading term is basically this expression here, is equation 24. Now, if expressed in terms of dr and opacity, then this equation can be written as, you see, this form, like this, equation 25. Now, from here we can get the energy flux using this relation. F is equal to 4 pi r square 0 to infinity and d lambda, equation 26. Now, this 4 pi r square comes from the integration over the spherical surface of radius r. Now, the precise value of f depends on the knowledge of the opacity as a function of lambda, right? But we can sidestep this issue by introducing a quantity called Roseland mean opacity. Now this is defined as this term, you see here, this is how we define this. So this is basically definition, equation 27. So with this definition, the heat flux can be basically expressed in this form. So this is the heat flux, right? Now what more? Of course, now we are going to use the Blackbody expression. So you must recall that B lambda is equal to U lambda C by 4 pi, and so this is basically recall, and also this d lambda is equal to A into T to the power 4, 29. So this was equation 28. So if we do this recall, then we will get the desired expression, and the expression is this heat flux. So this is the final form of heat flux, equation 30. Now it remains to find kappa average, this quantity, this average value of kappa, as a function of rho, t and x. Okay, now there exists lot of tools. You can check websites also, internet sources, to find this value of kappa average. Now let us talk about lower temperature. At lower temperature, such as those found near the surface of a star, there may be substantial fraction of bound electrons, and so the opacities due to bound and bound free interactions dominate. These are the most difficult opacities to compute, since they arise from millions of absorption lines from all the different species in the gas, and as a result, at low temperatures, kappa average must be computed numerically, and there is no simple asymptotic formula. What about intermediate temperatures, such as those found in the upper envelopes of stars? Now there, the gas becomes substantially more ionized, and bound free and free absorptions dominate the opacities. The mean opacities for these processes are proportional to, so basically, intermediate temperature, and here you see the mean opacity for these processes is basically proportional to this relation. This is very interesting, rho to the power T 3.5, and this is known as Kramer's opacities. Right, now the bound free opacity average, it roughly follows this relation. Now I am not showing you any detailed derivation, just giving you a result. Okay, minus 7 by 2 or 3.5. Now unit is meter square per kg. What about the free opacity? So free, this is roughly 2 orders of magnitude lower and has the value like this: z square by mu e mu l, again rho, t to the power minus 7 by 2. Unit is meter square per kg. Now what about higher temperature? At still higher temperatures, such as those found deep inside stars, where the atoms are all completely ionized, then the electron scattering is the dominant contributor to the opacity. As long as the average photon energy is well below the rest mass energy of the electron, then you see this kappa average of electron scattering is simply the number of electrons per unit times per the number of electrons per mass times the Thomson cross section of the electron. So we can write like this: Ne by rho sigma E, and this is basically Ne by rho into 8 pi. So I am writing the Thomson cross section E square by 4 pi epsilon 0 Me into C square, and this comes out to be 0.02 into 1 plus x. So you see, the total opacity is simply the sum of the individual opacities at a given temperature. Now, okay, so what next? Well, now that we have the opacities in hand, we can express the radiative heat flux in terms of either R or M. So, in terms of R or M, and upon doing that, you see, this is the relationship which we get, and that is basically equation 34 and also the fourth equation of stellar structure, and basically this is also the equation of radiative transport, equation of radiative transport of energy, right? So this is what we have derived today.